In this example, we consider again the issue of having non-constant coefficients. In fact, in this example, there are two non-constant coefficients, one with a y double prime and one with a y. It's important to note that the equation is still linear. With that in mind, we'll proceed to try to solve this by using Laplace transforms. And we're going to start off by taking the Laplace transform of the entire equation. We're going to break this down into the Laplace transform of the first term, which we'll do in detail in a second. And we also have 2 times the Laplace transform of y prime. Well, that's sy of s minus y of 0. We also have the t in front of this last term, so we'll take the Laplace transform of t times y. In a second, we'll do that stage by stage. On the right-hand side, we have the 0, so we keep the 0 there. Let's do the simple term first. The Laplace transform of t times some function is the same thing as negative the s derivative of the Laplace transform of y, and that is equal to negative y prime of s. We take the transform of little y of t, we get capital Y, and then we take the derivative. The more complicated function is over here, but the same first step applies. We have a t multiplier, so our transform is going to be equal to negative times the derivative with respect to s of the transform of y double prime itself, and that we can calculate it's s squared y of s minus sy of 0 minus y prime of 0. We know one of those values is 1. And we know the other, well actually we don't know the other value. We have to be careful here. This is not an initial value, but a boundary value. Somewhere later on the value is 0. To make the calculations easier to follow, we use the letter a here for now, and we'll use this boundary value later on to find out what a is. Now we can compute the derivative. We're going to have negative. The derivative of this term is a product rule, so we'll have 2s y of s plus s squared y prime. The derivative of this is simply 1, and the derivative of this actually turns out it's not going to matter so much because the derivative is 0. All right, now we can bring in all the terms we had before. We can bring this down and this down. We'll add our 2s y of s minus y of 0, which is 1, and we'll have our y prime of s here, all of that equaling 0. Now at this point you'll notice that our new 1 over t integration formula hasn't come into play yet. It'll sneak up a little later. For now what we're going to do is simplify this expression here and see what we get. Gathering the y prime terms, we have a negative s squared times y prime, and we also have a negative 1. For the y terms, we have negative 2 s's and positive 2 s's times y of s. And we also have some singleton terms. We have a negative negative 1. That's going to end up on the far side as minus 1 when it's done. And we also have a 2 minus 1. That'll be negative 2. It'll become a plus 2 on this side. That leaves us simply with y prime of s. Careful, this is y prime. Try to emphasize that. Is equal to positive 1. And here we can factor out a negative, so negative s squared plus 1 in the denominator. Well, this is something we've seen before. We'll continue it on the next page. We have y prime of s equals negative 1 over s squared plus 1. So if we want y of s, we're simply going to integrate both sides. But we're going to integrate with respect to that s variable. So we'll have the integral and the negative s squared plus 1 in the denominator ds, and that we've seen recently is this is the derivative of arctan, so the integral gives us arctan s back plus some constant. To find that, what we do is use the property that in our transformation we have to have y of s heading towards 0 as s tends towards infinity. That comes from our exponential order classification of functions. And if that's the case, then what we can do is sub in that value here and take the limit as s goes towards infinity of minus arctan of s plus c. And this we already know. We've seen this before. This is pi over 2, but there's a negative sign out front, so negative pi over 2. And at the end of the day, we end up with c is equal to positive pi over 2. So our y of s is equal to negative arctan of s plus pi over 2. Now, what in the world are we supposed to do with that at first glance? This is definitely not in our table of integrals. However, we can take a step back to a previous example to highlight what we can get from this. In an earlier calculation, we took the Laplace transform of sine t over t, and lo and behold, we had pi over 2 minus arctan of s. So if we do the inverse transform, we're going to get back to sine t over t. So based on that previous work, using the integral transform for the 1 over t f of t functions, we end up with y of t is equal to sine of t over t. Now just a quick reality check. Does that make sense with the initial and boundary conditions? Well, y of pi is sine of pi over pi, and that's 0. Notice on the 0 end of things, though, we can't actually evaluate y of 0. So the best we can do is take a limit as t approaches 0. And that would be the value of sine 0 over 0, which, if you use L'Hopital's rule, works out better than you'd expect and actually gives you a 0 value as well. Last but not least, we would like to confirm that our solution is actually correct for the differential equation itself. We just said y was sine of t over t. To sub that in, what we're going to do is plug it into the y's and y primes. We're going to need those derivatives then. The first derivative will be a quotient rule. We'll have cos t times t minus sine t all over t squared. And we're also going to need the second derivative, y double prime, and that will equal the derivative of the top, which is negative sine t times t plus cos t, and the derivative of the sine is negative cos t. That's the derivative of the top times the bottom, minus the top in brackets, all times the derivative of the bottom, all over the bottom squared, which would be t to the 4. We can immediately simplify the cos minus the cos. That's about all we can instantly simplify, so let's just rewrite that one more time. We'll gather as sine of t's. We have a minus t times t squared, so minus t cubed. We also have a sine t here, which would be positive, times 2t. For the cosine terms, we have negative 2t squared. And that's all over t to the 4. We're now mostly ready to sub into the initial equation, especially the left-hand side, and see if things cancel out the way we're hoping for. So, what do we get there? We're going to have t times y double prime. So that's basically going to get rid of one of our t's in the denominator here. So I'll have sine of t minus t cubed plus 2t's plus cos of t times minus 2t squared all over t cubed, collectively ty double prime. Then we'll add two y primes. Our y prime is here. That's a cos of t times a t minus sine of t all over t squared. And then we'll have plus t times y, which is just sine of t when we're done. That's our left-hand side. And what does that equal when we simplify it? Well, we end up with sine of t cubed over t cubed, so that's minus sine of t. We end up with sine of t, two of them, 2 sine of t over t squared. But if we scan along, what other signs do we have? We have, oh wait, minus 2 sine of t over t squared, and plus a sine of t. Excellent. That takes care of all the sine terms. For the cos terms, we end up with cos of t, minus 2 of them, and it's over t by the time we're done, t squared over t cubed. And over here, what do we have but plus 2 cos of t over t's, and all of those cancel in pairs, there and there, there and there, there and there, and we get 0. So we get ourselves a big check mark for correctly finding the solution, the non-obvious solution to this differential equation.